Hello gals and guys, Mr. Ambrose here with the second of my AP exam review videos. Today I want to explore in a little more detail the methods of integration that you guys learned this year. And I hope that, obviously if you're watching this video, I'm assuming you watched the video from yesterday. And so whether, you looked at the problems I did in the video, or you maybe looked at a problem or two that I assigned as practice problems, I hope you start to see the complexities that could be thrown at you for this AP exam and the necessity to just try to do your best to just, keep up with what I'm doing and try to do, at least some of the problems that I assigned as practice problems. So with that being said, I'm going to jump right into example 1 here. We want to consider this particular function, g of x, that we have as defined as such, where c is a constant and c is less than 0. We want to find this particular integral, and because of the infinity up on top, this is an improper integral. So we want to find this improper integral in terms of c, where h of x is equal to 6c. So, as I mentioned, this is an improper integral, and as you learned this year, when you have an improper integral, you definitely have to introduce limit notation, and you can choose whatever variable you like. I'm going to use my favorite variable, Mr. Smiley Face, and we replace the infinity with our variable. And now I could write g of x here, but because g of x is equal to this function, I'm going to put that in here. And furthermore, because h of x is equal to 6c, I'm going to put 6c in for that h of x as well. And so now we have this here, which we have to try to evaluate. Now, this part here is a definite integral, and as you learned this year, to evaluate any definite integral, we have to try and find the antiderivative of this integrand. Now, the methods of integration I discussed in my first video. Substitution isn't really going to work here, and I've never really seen a voodoo integration of a fraction. So remember, there was another method of integration, partial fractions, that helps us break a fraction like this down to smaller fractions that we can then easily integrate. And so that's what I'm going to do. And to help find that antiderivative, I'm just going to go off to my next page here, off to the side, and actually I just want to break down the fraction. So I'm just going to try to take my integrand and perform that method of decomposing this fraction into two smaller fractions. And it's nice enough for us that the denominator is already factored, so we can write this as the sum of two fractions. The first fraction has denominator x plus 2c. The second fraction has denominator x minus c. And if you recall, the numerators, we don't know what they are at the moment, but that's actually what we're going to go and try and solve for. So now, to solve for what these a and b numerators are, I'll quickly multiply each fraction in my equation by this denominator of my original fraction. All right, and when we do this, what happens very nicely is that this first fraction, basically these factors will just cross out and we'll be left with this numerator 6c, and then this second fraction in our equation, the factors of x plus 2c, reduce, so we're left with a times x minus c, and then this last fraction, the factors of x minus c, reduce, so we're left with b times x plus 2c. And now, from here, to again help solve for a and b, if you recall, we can let, I should say this equation should be true for any x value. So we can let x be equal to any number that we would like. And so if perhaps we want to get rid of this a to help us solve for b, I would say that we would want x to perhaps be equal to c, so that will get rid of this whole expression here and leave us with an equation that we can solve for what b is equal to. And so doing that, we would have 6c would equal a times c minus c plus b, and x being c, I'd plug c in for x. We'd have, therefore, c plus 2c in its parentheses. And if we simplify things, again, this is just going to become 0, and this is just going to drop out. And then here we have b times c plus 2c, but c plus 2c is just 3c. So we would have 3cb, and then solving for b, we can just divide both sides by 3c and get that b is equal to 2. So this fraction here would be 2 over x minus c. And then if we want to solve for what a is, we would want to get rid of b, and we can do that by perhaps letting x equal to negative 2c. And so now, if we plug in negative 2c in for x in this equation, we would have 6c equals a, parentheses, 2c, negative 2c minus c plus b times negative 2c plus 2c. And again, this second term is just going to completely drop out because this is going to be 0. But over here we have negative 2c minus c, which is negative 3c. And so if we divide both sides by negative 3c, we would see that a is equal to negative 2. So this fraction here becomes negative 2 over x plus 2c. And I don't know if I want to, actually, I'm going to do it over here instead. If I now want to integrate this 6c over x plus 2c times x minus c, right, we can do that by, again, breaking this fraction down into these two smaller fractions. So the first fraction had a, which was negative 2 over x plus 2c. This would be negative 2 over x plus 2c. And then our second fraction was b over x minus c, where b was this 2. So this will be 2 over x minus c. So 2 over x minus c. And now I claim that this will be easy to integrate. Basically, the negative 2 can be pulled out in front. And remember, I'm going to split this up into two integrals, where this first integral, I'm going to pull the negative 2 out. And then my second integral, I'm going to pull out this constant of 2 in front of my integral with integrand of 1 over x minus c. And now, looking at these separately, this integral, or this integrand here, is just 1 over x plus 2c. Don't get thrown off by the 2c. That's just a constant. And so, since we really have down here an expression with x to the first power in the denominator, I claim that the antiderivative will be the natural log of the absolute value of x plus 2c, right? Because if we derive the natural log, remember the derivative of natural log is 1 over this argument, and so that would give us this here, and then we would have to perhaps do a chain rule, derive the inner function in terms of x, but I claim that that just would be 1, because that's the derivative of x, and the derivative of 2c is just 0. So this is the antiderivative of our first integral, and then the second integral will have a similar antiderivative, but this will be the natural log of the absolute value of x minus c. I'll just write plus c there. And again, this antiderivative of this is natural log because this is x at first power, and right, if we were to check our answer and derive this here, once again we would get 1 over x minus c times the derivative of the inner function, which is just 1. So this is our antiderivative to this expression, and so now we can take this and use that to help evaluate this whole limit expression. So if we do that, it's going to carry through my limit notation. And again, we had that, or actually, I should say, to help with evaluating what ultimately is going to happen here. Actually, I'll do it right over here. We're going to have -2 natural log absolute value of x minus 2c, sorry, x plus 2c, plus 2 natural log absolute value of x minus c, and that's our antiderivative, and then we have to evaluate that from these two limits of integration. But now, as I'm looking at this, one of the things that's going to happen here is that we're going to ultimately have to plug in infinity in for Mr. Smiley Face, which is going to go into these x's. And the problem's going to be is that essentially both of these arguments are going to be infinity. And the natural log of infinity is infinity. So to help with evaluating all of this, I'm going to actually, before I just plug in my limits of integration here, I'm going to truncate these two natural logs into a single log of a fraction of this argument of x minus c over this argument here of x plus 2c. And just now write in my my limits of integration. And the reason why it's this argument over this argument is because we can think of these two natural logs as this log minus this log with the 2 out in front. And when you had a difference of two logs, we can truncate them into one natural log as a quotient of the two arguments, with the first argument being the numerator, and then the second argument of the natural log that we're subtracting at the denominator. And so now I'll plug in my limits of integration. So put Mr. Smiley Face in first. And then plug in 1 minus 2c into this here for x. And in the numerator, when we do that, we would have 1 minus 3c. And then in the denominator, when we plug 1 minus 2c in for x, the negative 2c and the positive 2c will cancel each other out. So we just be left with this here. And so now to evaluate this particular limit, now when we plug in infinity in for Mr. Smiley Face, inside this expression, we're getting infinity over infinity. And I claim we can sort of just focus in on this here because, well, first of all this here is just a constant. I know c is a variable, but we would treat this as a constant as Mr. Smiley Face is running off to infinity, so we don't have to worry about this. And over here, we have this composition of functions. And so because of this composition of functions, with this fraction inside the natural log function, remember that when you have a composition of functions, provided that the outer function is continuous wherever we're really evaluating the inner function at, then we can just focus in on the inner function as Mr. Smiley Face goes off to infinity. And again, this here is going to infinity over infinity. And so off to the side, if we consider the limit as Mr. Smiley Face approaching infinity, Mr. Smiley Face minus c over Mr. Smiley Face plus 2c. Well, because we're getting infinity over infinity here, we can do L'Hopital's rule to help with evaluating this particular limit. And because it's in Mr. Smiley Face that is approaching infinity, we would derive with respect to Mr. Smiley Face here. And so that would give us 1 in the numerator, because remember, c is just a constant, and the derivative of constant is 0. And the derivative of Mr. Smiley Face would be 1. And in the denominator, we would also get just 1, because that's the derivative of Mr. Smiley Face is just 1, and the derivative of 2c is 0. And so now we have this expression 1 over 1, and as Mr. Smiley Face raises off to infinity, this is just going to stay put at 1 over 1, which is just equal to 1. And so what we get here for the value of this entire limit would be 2 natural log of the absolute value of 1, which is just 1, minus 2 natural log of this expression here, which I'll just simplify because this is over 1. I'll just write as 1 minus 3c in absolute value as the argument there. And so now, because I've evaluated everything calculus-wise, my improper integral and my limit, and these are just basic expressions that I can evaluate on a calculator, I claim that this would be my final answer. So it took me a while to get through this particular problem. And so in particular, this highlighted the evaluation of an improper integral, which you should be able to do, as well as breaking down fractions into smaller fractions, in particular to help us ultimately find antiderivatives. And so these are all things that you learned and that you could be expected to apply in a problem like this here. And once again, hopefully you recognize that there's no way that you really could have perhaps evaluated this using your Inspire calculator. So again, the College Board is really going to find ways to test your understanding of the material that you learned this year, and your calculator really is not going to play a big role in helping you with answering these problems. So I'll give you some more practice problems to practice, evaluating improper integrals and also doing this partial fraction decomposition method of helping to find antiderivatives. As always, if you have any questions, please don't hesitate to, send them my way, and I'll try to get back to you as quickly as possible. And as always, please take care, stay safe, and I'll talk to you soon.